Hello friends, so let's talk about the sigma level. So far we've used potential capability and overall capability to determine how processes perform relative to specifications. We can also use another metric called sigma level to quantify capability. Consider the ABC paint company, uh, which produces acrylic paint for artists. Paint viscosity is important to artists because it affects the thickness, transparency, and overall visual effect of painted works. So when artists purchase a certain type of paint, they expect the product to have a specific effect on their canvas. To study their process, a worker at ABC samples one paint container from each of 200 batches of material. They assume that the batches are homogeneous, so a subgroup size of 1 is adequate. They measure paint viscosity in centipoints. ABC must manufacture its paint product to have viscosities between 30,000 and 45,000, 30,000 and 45,000 centipoints, 45,000 centipoints. So how capable is this process at producing paint with the correct viscosity? We can assess the capability of this process using a sigma level capability index, also called the Z-score or benchmark Z. The sigma level is a single number that accounts for defects both above the upper specification limit and below the lower specification limit. To illustrate, so let's calculate the sigma level of the viscosity data collected at ABC Paint Company. We use properties of the normal distribution to calculate the sigma level. For this example, the mean is 40,648 and the standard deviation is 4,294, which gives us this normal curve. The shaded area above and below the specification limits show us the percentage of paint viscosities that we can expect to be out of specification. We will first calculate the percentage of viscosities out of specification using z-scores. Recall from chapter 2 that a z-score is the distance of any value from the mean in terms of standard deviation units. To illustrate, let's calculate the percentage beyond the upper specification limit. The formula is shown here, giving a z-score of 1.01. Using the standard normal distribution, we calculate the area above the z-score that corresponds to the upper specification limit. This area is 15.54% of the distribution. And let's now calculate the percentage of viscosities that we would expect below the specification limit using the standard normal distribution. The z-score that corresponds to the lower specification limit is 2.48. So and this area is 0.66% of the distribution, we would expect to 0.66% of paint samples to have viscosities below the lower specification limit. The total percentage outside of spec is simply the sum of these two percentages. Once we know the area that is equal to the total defect, we can calculate the sigma level. We combine the expected percentage of defects out of specification and put them on one side of the mean to calculate the sigma level. The sigma level corresponds to the number of standard deviation values that would fit between the mean and the point where the defects start. The sigma level is calculated using the inverse cumulative distribution function. While the cumulative distribution function gives the area under the probability density function, the inverse CDF does the opposite. It calculates the value associated with an area. We can use Minitab or Excel to compute this for us. In this case, the z-score that corresponds to an error of 0.62 or 16.2% defect is 0.983. This is the sigma level of the process. Notice the sigma level increases as the number of defects decreases. Therefore, a higher sigma level indicates a more capable process. Although different organizations strive for different sigma levels, values of 4.5 or more are generally considered good for a sigma level, assuming that the process is in a state of statistical control and that the viscosity data are normally distributed. So, is the process at ABC capable? For this process, the sigma level is 0.99. It seems that there's too much variation in paint viscosity, which would result in too many samples that are thicker or thinner than desired. ABC might attempt to reduce variation in the process. Sigma level like CPK and PPK measures the process relative to specification limits. All of these metrics have no units, so we can interpret them for any process in an organization. The preferred capability index can depend upon the application, industry, or even the organization where the process is measured. In some instances, one measure may be more meaningful than another. Let's review. The sigma level uses z-score to estimate process capability. Higher sigma levels indicate a smaller chance that our process produces parts our services that are outside of the specification limits. Thank you for your listening. In the next lesson, we'll talk about the process capability for non-normal data.